Welcome to note set number 20, where we'll continue our discussion of the DFT machinery. And in particular, we'll talk about some of the symmetries involved with the DFT. So these are properties that can be taken advantage of or used to achieve certain efficiencies or effects when using the DFT for different algorithms. So these are just kind of characteristics that just kind of stick in the back of your mind, and you go, oh, okay. At some point you're developing something, you go, wait a minute, wasn't there a symmetry or something, and maybe I could use that to my advantage here. So let's take a look. So just because of the fact that the DFT and the IDFT, as we mentioned last time, when you think about them, you think about in the real setting, it's a finite chunk of data in the time domain. It becomes a finite chunk of data in the frequency domain. But as I mentioned last time, you really should be thinking about that finite chunk, each of those finite chunks, as some just one period in some longer periodic mathematical entity. And those other periods can come into view due to operations that you do on the signal in one domain or the other. So for example, if you modulate, if you multiply in the time domain by a complex exponential of the proper frequency, you'll see a circular shift in the frequency domain. And we've seen other things like that. So anyway, that nature gives rise to these circular symmetries, and or it not enables, but require us to think about symmetries in the context of this circular nature. So we typically have odd and even functions for regular functions, and now here with these periodic or circularly viewed functions, we need to think about, rethink what does even function mean, what does odd function mean. So we will say that we have a circularly even sequence if the following is true. So we'll say that x of n has to be equal to x of capital N minus little n. And you can see that that really just comes about from saying that the periodic extension is itself an even function just defined the normal way. Once you recognize, set this characteristic in place, then it's easy to verify that that follows, and from that we end up getting this kind of idea. And we can also see what that means in this circular viewpoint. So we're saying that if we evaluate this function here, we would have that x1 and x of 7, this is for the n equal to 8 case, have to be equal, and so we can see that that means we have this symmetry here, which I've illustrated with that that first curved arrow, and then we have x2 and x6, so these things must be equal to each other, x3 and x5, and the formula even gets that x4 must equal x4, and so that's certainly true for the case when you have an n equal to an even number, which will mostly be the case that we're interested in, because we will almost always limit ourselves to powers of 2, although we don't necessarily have to. That's driven largely by the FFT algorithm being most useful for powers of 2. So for complex signals, we could define conjugate even signals, and so that just includes this conjugation. So this just extends the idea of an even sequence into these kind of circular sets. And likewise, we have circular odd sequence. And so, all the same kinds of ideas we we get there by doing the periodic extension and defining odd symmetry in the standard way. That then illuminates how to think about it in the context of an n minus little n, and so then that carries over into this view. And I'm just pointing out here that this does not start at 0 with our definition. And so we have the same kinds of pairings here, and the only difference is that there's a negative sign involved. Now when we get to this one, the only way something can be equal to its negative is if it's 0. So that tells us that for odd symmetry with an even number of terms, that must be 0. And we can extend this to the concept of conjugate odd signals. All right, pretty straightforward stuff, just expanding the ideas. And for standard even and odd functions, we have a result that says that we can break down any function into a sum of an even part and an odd part. And we can do the same thing here with this periodic extended versions. So any periodic extended function can be broken down into one term that is periodic and even, one term that's periodic and odd, and in fact we can find those two individual parts from the original signal by just doing these operations. And it's pretty easy to verify that each of those it has its stated characteristics. So the first one is in fact even, second one is in fact odd, and obviously if you add all these together the way that we show above, we see that those parts cancel out, and we're left with 2 times 1/2 xp, so we get back xp. So again, pretty easy generalization from what we have for standard functions. So now we want to look at some of the properties of the DFT that come from symmetry characteristics. So we're going to, in general, assume that the signal is complex valued, and obviously the DFT itself is complex. So here's our definition of the DFT. And all we're doing here is plugging in explicitly that the signal is allowed to have a real part and an imaginary part. So now we've got one complex number in rectangular form. We've got another complex number in rectangular form. So if we take an individual term of that sum, multiply it out, we'll get a real times a real. We get an imaginary times an imaginary. And then we get 2 real times imaginaries. And so if you group all those things together, you'll get the real part and the imaginary part. And in fact, then when you extract that, you can find that the real part of the DFT ends up looking just like that. So that's just extracted from that expanded summation. And the imaginary part of the DFT looks like that. And so these things are used a lot when you might be in the development of a result or something, and you might say, gee, I just really need the real part here. And so what would that look like? And so now you have a result that tells you what that looks like. So I know that this looks like it's just a lot of dry properties, and to some degree you're right. It is just kind of learning a lot of dry properties, but it's kind of like moving to a new city. You kind of walk around with no purpose, just noticing where things are. There's an interesting building. Oh, look at that little side street there. I've never noticed that before on my first outing, and now I'm noticing it on my second outing. So, you're not really doing anything that looks like it's important, but later on when you're traveling around that city, you go, hey, I remember that, and I can exploit that. Okay, similar kind of thing. If we do the same kind of thing with the inverse DFT to write the original signal, we can find that the real part and the imaginary part of the signal can be found using formulas that look like that. Okay, so now that we have these general results written out, we can start asking questions. Well, what happens if x of n is real valued? Well, if x of n is real valued, let's look at the complex conjugate of our DFT. So we just put in our DFT result and we put a complex conjugate on it. And then we pass the complex conjugate inside. So notice that our J has now become positive. See if I can get rid of that stuff. Nope. Let's see. There we go. Okay. So our J has become positive, and we pass the complex conjugate through to X, but we said that X is real valued, so conjugating it has no impact on it. And so what we see here is that for a real valued signal, if we take the complex conjugate of the DFT, it's the same as indexing it backwards. But remember that the periodicity of the DFT allows us to write this indexed backwards as indexing from the other end. So we can recognize that when we have a real valued signal, we're used to a certain symmetry around DC, but for DF, that's on the DTFT and the CTFT. For the DFT, as we're speccing it here, we're just looking from 0 to 2 pi, and so that's why we have this characterization. Once we do an FFT shift, though, then we can more easily exploit this kind of viewpoint. So, so this just states that property that if we conjugate the DFT, it's like doing a timer, flipping it around DC, but it's also like counting off from the other end. So from this equation, we can see a few things. If we plug in k equal to 0, we can see that we get that the conjugate at 0 must be equal to the non-conjugate at n. That together with the fact that those two things must be equal due to the periodicity of this tells us that that the zeroth coefficient, the zeroth DFT coefficient, must be real valued. And again, this is for real valued sequences. Similarly, we can see that halfway also must be real. And so what these results lead us to is that the magnitude must be circularly even, and the angle must be what I say sort of circularly odd. So I say sort of just because it doesn't quite exactly meet the requirements that we had. So that the angle of at halfway through doesn't have to be, it could be m times pi, so it's not quite exactly how we define circularly odd, but it's pretty close. So this is just a picture of this. So the red shows one cycle. The two blue on each side show the adjacent cycles. And we're just seeing the symmetry for a real signal. So the top plot is the magnitude, the bottom plot is the angle. And we're just seeing this kind of symmetry here that we just described. So just an example, and then this is an example out of the textbook, and there was a little error in the textbook, so just pointing that out. So my example on the previous slide was kind of a made-up one, very small n value. This is a larger n and is a more actual result. So it gives you a little better feeling for what things really look like. So now if we say not only do we have real valued signals, but they are circularly even signals. From x of n being real, we already saw that we got those two results. Well, in general, and so x of n being real means that these two things will be equal to 0, so these terms will go away. So once we have that, then we can focus on the first term in each of these. Let me get rid of that. So we can now focus on this, and we can focus on this. And what we see in the second of those is that sine is a circularly odd function, and xr we are assuming is circularly even. And we know that an even times an odd equals an odd, and then summing up an odd gives us 0. So this boils down to this result, which says that for a time signal that is real and circularly even, we can reduce the equation for the DFT to something that looks like this. So we no longer need complex exponentials, we only need a cosine. Similarly, going backwards, we can write the inverse DFT this way, and we just showed that the DFT for this case was real, so those two terms will go away since the imaginary part is equal to 0. And then we again, this part will be even, since we just showed that it was even. So this term will go to 0 because we have an even function times an odd function. And so that leaves just this part. So x of n will just be equal to an inverse DFT that uses just the cosine part. And we should get back something here that is real and even. Okay, last, we'll just finish off with the dual of that, real valued and circularly odd. We won't go through all the development of it, but we can see that now we get results that use sines instead of cosines. So the results for circularly even, real and circularly even, gave us cosine functions there, and circularly odd gives us sine. And if you look in the textbook, table 7.1 has a bunch of symmetry properties, and I'm not going to go through all of those. So again, like I said, yeah, these are kind of just stupid and boring properties, but they're things that it's worthwhile keeping in the back of your mind. You don't have to memorize the exact forms of these, but you should, tuck in the back of your mind and not that far back, things like, yes, I should keep track of what happens when one thing is real or one thing is imaginary, or when something is even or when something is odd, those kinds of things. All right, we'll stop there, and I'll see you in the next note set.